Alright, so we're going to start chapter 8 of the Further Math series. This is going to be looking at recursion and finance. So the first topic will be taken from the textbook, which is 8A. We're going to look at review of sequences. So if Tn represents a term in a sequence, then Tn plus 1 represents the term after Tn, hence Tn minus 1 represents the term before Tn. So when we're talking about a sequence, we've got, for example, let's say even numbers. So 2, 4, 6, 8, 10. And if I asked you, our starting point was 6, right? This is what we could call Tn. What this statement here is saying, I'm just trying to explain this particular part. When we've got Tn plus 1, that's just saying the next term. So Tn plus 1 would be 8, and the previous term would be Tn minus 1. So the whole Tn thing is supposed to just represent the position and the actual term, I guess you could say that we're trying to, that we're given in this case. All right, so n represents the actual position, Tn represents the actual value at that position, at the nth position. So it says the general form for a recurrence relation. So a recurrence relation is a particular rule that describes a sequence of, I guess you could say, a sequence of numbers. So say the general form of a recurrence relation is given by this. This should also say where t0 equals a. Okay, I'll explain that in a moment. Then the sequence for Tn plus 1 is given by. So what this is saying is that if you are given a sequence, okay, you're given a number 0 or a term 0. Okay, to find out the next number, okay, the next number in the sequence, what you need to do is you need to multiply by b, and you need to add or subtract a value c, and once you do that, you'll get your next particular answer, t1. And to get t2, you need to use your answer from t1, and then you would need to multiply that by a constant b, and then, so not a constant b, but a multiplying factor b and a constant c, to get your answer for T2, and likewise for T3. So all the sequential terms depend on the previous term. That's what recurrence relations, I guess you could say, the whole point of that is. So, however, it is important to note, in order to calculate the values of successive terms, that T0 equals A needs to be defined. So whenever you're asked to calculate or to find the recurrence relation, it's important that you understand there are two parts. There are always two parts to this: the rule and the starting point. Okay, it's always important that you always define these two. That's how you, generally the way you can work out what the starting value is if you have the term T0. T0 means the initial value. Let's move on to the next bit. Arithmetic and geometric sequences. An arithmetic sequence is a sequence of numbers such that the difference between the consecutive terms is constant. So, in other words, it's saying that the next term compared to the previous term, there's a constant number that goes up by even amounts. So, for instance, the sequence 5, 7, 9, 11, 13, 15 is an arithmetic sequence with a common difference of 2. Likewise, if you have the sequence 1, 6, 11, 16, 21, this is also an arithmetic sequence because it's going up by even amounts, 5, and the common difference would be 5. So relating back to the general formula, Tn equals 1, such that the arithmetic sequence results when b equals 1, results in that. So you can see from the difference between this sequence here and this sequence is that the B, I guess you could say, has disappeared. But there's a reason why the B has disappeared, because this particular part, there is no multiplying factor between the terms. Since the common difference is constant, this here, the value of B is equal to 1. So in other words, this is the sequence that you should be referring to with arithmetic sequences. T0 equals A. The C term determines whether the sequence increases or decreases in value, depending on the sign. So if you have a sequence that's going up, like this one here, 1, 6, 11, 16, and 21, this would have a plus sign. Okay, but if you had a sequence that was going, it was decreasing, say for example 100, 90, 80, 70. Okay, this sign here would be negative. Okay, in fact, this sign would be plus 5 for this part here, and this for this sequence, it would be minus 10. So C pretty much tells us the common difference. So let's have a look at an increasing sequence and a decreasing sequence. So you can see with this one here, you've got, as I said, the general formula or the general recurrence relation for arithmetic sequences. The B value is not there because it is an arithmetic sequence, I'm telling you that. Tn plus 1 is equal to Tn plus 3. So the next term is equal to the current term that you've got plus 3. So we start off at negative 2. This is our starting point. Okay, and we're adding 3 every single time. Adding 3, adding 3, adding 3, adding 3, adding 3. And that's why we've got the plus 3 there. This one, we start off at negative 2. Okay, so that's negative 2 there. And we're taking away 3 every single time, and you can see from this point it's a decreasing sequence. Okay, so it's worth noting that decreasing doesn't fall far from what you've learnt in the past. Decreasing goes down that way, and increasing goes up that way. Okay. A geometric sequence. So this is the other thing we have to be familiar with. Geometric sequences, it's where the multiplying factor, there is a fixed multiplying factor. So with arithmetic sequence, there was a common difference. Geometric, there is a common factor. You've got this example here, 2, 6, 18, and 54. So the common ratio is 3. So to get from this to this, to this, to this, to this, to this, you times it by 3, times it by 3, times it by 3. Okay, whereas the other ones would be plus minus, this one's times or divide. Relating back to the general formula, Tn plus 1 is equal to B times Tn plus C. Arithmetic sequences result when B does not equal 0 or 1. Because if it equals 0, you don't have a multiplying factor. If it equals 1, it becomes an arithmetic sequence. A value of 0, a B is between 0 and 1, results in exponential decay of successive terms. And the value of B is greater than 1 results in an exponential increase of the value of successive terms. B denotes the common ratio between each successive term. So B is the common ratio. So I've given you an example here of the two types of sequences that you can see. If you have a value of B that's greater than 1, okay, this increases in that particular shape. So geometric sequences have that curved-like shape. The starting value is 2, and each time I go to the next term, I'm going to multiply it by 3. So you can see it jumps all the way going from 2 to the 5th term would be around this point here. It's in the hundreds. If you have a value that's in between 0 and 1, so decimal, okay, and you start off with the number 2, this rapidly decreases or decays. So it would have this particular shape, and that is geometric sequences. Okay, so we'll end it at that point, and we'll move on to recurrence relations for the next bit.